Hello, David here, and welcome to this tutorial, where we will learn how to use the Python editor to create Python script behaviors in Visual Components. When following any tutorial, check the lesson on the Visual Components Academy, and if the Download Files option appears, you can download the example files. We will learn how to interact with the simulation environment by using Python script behaviors that are saved together with the components. We will get an overview of the Python version 2.7 objects, learn how to use snippets, and create a simple script to add functionality to a component. Note that while it's also possible to use Python scripts as commands to extend the user interface capabilities, in this tutorial we will not cover the use of commands scripts. We will begin by selecting which Python script editor we want to use from the Backstage options. In this tutorial, we will use the internal editor. Let's begin by selecting this conveyor tracking based component, and to create a new Python script, go to the Modeling tab, then from the Behaviors menu, select Python script, and the internal editor opens in a new window. The root node in the component graph panel on the left will expand to display the component's behaviors, where we can see the behavior we just created, and where we can also find any existing Python scripts. So we will look for a Python script that we want to edit, and double-click on it to open it in the editor window. As we can see, it's possible to open multiple editor windows at the same time. When using the internal editor, we can set the font size using the Ctrl and plus and minus keys on the keyboard, or using the Control key and our mouse wheel. And we can use the mouse wheel to scroll up and down. Line numbers appear on the left, and if we want to jump to a specific line, we can use Ctrl plus G on the keyboard. The internal editor toolbar includes tools for compiling, debugging, and editing a script. To learn more about each toolbar item, we can visit the Help tab and click Help. Or in the Modeling tab, we can click away from the editor and then press the F1 key to access the Visual Components Help documentation. Let's close the existing script window and continue working on the Python script behavior we just created. The internal editor supports the insertion of code snippets. To add a snippet, use the snippets control from the toolbar or the keyboard shortcut Ctrl plus J. And from the drop-down menu, double-click to add _comp app sim, which allows us to access the most used object handlers. A practical way to test our code is printing. We can print a string comp object within single quotes, then add a comma and the comp object. If the simulation is not running, we can manually compile the code while editing the script. So to view the printing in the output panel, we need to compile our code using the compile control. When we compile, only the code in the global scope gets executed, where the global scope includes all lines of the script that are not inside any function or class. So if we add a print comp object inside this function, when we compile our code, it will not be printed. Component scripts will also get compiled automatically when we add them in the 3D world, for example, when adding components from the eCatalog, when we copy or clone a component, or when we reset the simulation. So if we play the simulation, then pause it and make a small edit to our script. When we reset the simulation, the script gets compiled. And if we go to the Home tab and clone the component, we will get another print of another component object in the output panel. We can now delete the copy of the component and right-click on the output panel to clear it. And returning to the Modeling tab, let's say we would like to hide or change the radius of the sphere. How could we do that? First, we need to get the handle of the sphere feature. To get the handle, we can simply drag and drop elements from the feature tree in the component graph panel into the editor. So let's do that for the sphere. Or holding the Shift key, when we drag and drop elements, we can get a smarter getter code for that same element. Now let's use this getter code and then save the object into a new sphere variable to access it later. Make sure the line is declared after the component handle on line 2 in this script. The internal editor allows you to use autocomplete to complete a line of code. When you write, for example, sphere, and add a dot notation after the object, a drop-down menu of its properties, methods, and events appears. And after the menu is closed, you can reopen it anytime by pressing Ctrl+space. And from this menu, we can find, for example, visible. We can scroll the list using our mouse wheel, keyboard arrow keys, or find using autocomplete. So type V and double-click the item or use the Enter key to insert it. And when we insert it, a small documentation box appears, which describes the property, method, or event we selected. To hide the ball, we can set the visible property to equals false. And after compiling, the visible property in the component properties on the right appears unchecked, but the change is not reflected in the 3D world. To see the effect in the 3D world, we must rebuild the component and then render the 3D world. Comp object has a rebuild method, so type comp dot, and to find the rebuild method using autocomplete, type R. Note the naming convention of the method, all letters in lowercase, followed by the parentheses. App is the object type for the main application, and it has a render method to render the scene of the 3D world. And now, after compiling, the ball should be hidden in the 3D world. Let's make the ball visible again by changing the visible property value to equals true, and we will also change the radius. To copy the currently selected line, use Ctrl+D on the keyboard. And on this new line, rewrite visible as radius, a property of the sphere feature, which in this case is not available from the autocomplete. And set the value to 75. And compile once more. The ball should now be visible in the 3D world. The event handlers are default functions that have been registered to certain events, meaning that when the event happens, the function is called. And when we create a new Python behavior, the default script contains the two most common handlers, which are onSignal and onRun. VCScript also provides other events that can be used in scripts to respond to various events during simulation. In the Python API section of the Visual Components Help documentation, we can check the reference guide under VCScript for more detailed information. The most common are onRun. This is the main program that runs during the simulation. OnFinalize. This handler is called when a layout or component is loaded into the 3D world. OnSignal. This handler is called when a signal is received. OnSimulationUpdate. This handler is called when the simulation is updated, and the event handlers that are associated with the simulation player: on start, on run, on stop, on continue, and on reset. For example, on start is called in the very beginning of simulation start. To prove that, let's add the onStart function to our script. The order of the functions in the script is not important, but for clarity, we can add it before the onRun. Let's then print SimStarted in the onStart function. Then print SimRunning in the onRun function. Then we can compile the script and click play to run the simulation. As soon as we run the simulation, from the start, the prints can be seen in the output panel. Then resetting the simulation, onRun is the main scope, because it is the only scope that allows blocking, such as delays, servo motions, conditions, and other time-consuming methods. Also, it has typically a never-ending loop with the main logic, where we continuously do some actions. Let's add a loop while sim.dot is running. After we type the colon, we can press the escape key or mouse click to ignore the drop-down menu. Inside the loop, we add a time-consuming action, for example, a delay of 1 second. Then let's print the simulation time every second by adding sim.simTime. Then compile and run the simulation. Then pausing the simulation. Another common event is to get a user's input on changing a component property's value. Let's create a simple example by writing a script to create a ball radius property and define a function reacting on the property value change. We will first use the snippet _property onChanged. Remember that we can also use the keyboard shortcut Ctrl+J. This snippet will create an event function for us, event_func, a property handle myProp, and then register the property onChanged event to the function call. Let's now change the property handle name to ball radius. The ball radius property does not yet exist, so we can add a line of code to create it in the Python script, in case the my_prop variable is none. The comp object has a method called createProperty, which takes as arguments enumeration type and string name. The type can be checked in the constants in the Python API help. From the VC script topic, we can navigate to methods, and from the getComponent method, click the return type VC component. And from VC components methods, we can find createProperty and check which enumeration type constants are used. And in property constants, we are looking for the real value of ball radius, so the property would be VC_real. Let's type it as the first argument. The second argument is the name of the property, which is in this case ball radius. To change the ball radius, according to the component property value, we must select lines 8, 9, 10 and 11 of our code above. Then cut using Ctrl+X and going to line 23, press enter for a new line and use Ctrl+V to paste them under the event function. Then select lines 25, 26 and 27 and click the Tab key to add the line indent. The arg is the argument passed to the event function, in this case the property object. To change the sphere radius value dynamically, we must replace the hard-coded value of 75 with the property object's value as arg.value. Then let's reset the simulation to compile the code and test whether our script reacts on the property values change. So now we can check the component properties. So in the 3D world, double-click to select the link and double-click again to select the component and view the ball radius property we added. Then edit the property to 100 and then to 50. And now we know the code seems to work because the ball changes radius in the 3D world when we change the property value. Brilliant! And this will conclude our tutorial. And finally, as a homework challenge, can you make a button property called hide show ball and write a script to hide the ball if it is visible and show the ball if it is not visible? Then check the lesson downloads to see if you got it right. Thank you for watching.